is Arina binti Ramli.
My name is Alia Masarah binti Ahmad Sarah.
My name is Nur Ashika binti Abdul Aziz.
My name is Nur Sofia Batrisha binti Jamri.
I will introduce an overview of solar energy system. Solar energy system harness sunlight to produce electricity or heat. There are two main types. The first one is photovoltaic, which is PV. System solar use panel made in semiconductor material, which is silicon, to convert sunlight directly into electricity. Commonly used in residential, commercial and utility scale power generation. The second one is solar thermal system. Use mirrors or lens to concentrate sunlight to generate heat, which is then used to produce electricity, like concentration solar power or CSP plants, or for direct heating, often used in large-scale industrial or grid applications. Next is common challenges of solar energy system. The first one is intermittency and weather dependence. Solar energy generation is variable, limited to daylight hours and affected by cloud dust or seasonal change. The second one is energy storage. Efficient and affordable energy storage like battery, molten salt is needed to ensure a continuous power supply during non-sunny periods. The third one is land and space requirement. Large-scale solar pumps need significant lands, which can lead to habitat disruption or land use conflict. The fourth one is efficiency limitation. PV cells have theoretical efficiency limits. Thermal loss also impacts solar thermal system. And the next one is initial cost. High upfront cost for equipment installation and infrastructure, although long-term operation costs are low. And the next one is material and manufacturing impact. Production of PV panel involves mining, energy use, and sometimes hazard chemical. Recycling and of-life panels is another concern. And the last one is grid integration. Integrated variable solar power into existing electrical grids require advanced load balancing, smart grid technologies, and possibly storage solutions. Next, we move to thermodynamic principle. First law of thermodynamics. Application to solar energy. In PV system, sunlight is converted into electricity. In solar thermal system, solar radiation is transformed into heat energy, which may then be used directly, such as water heating, or converted into mechanical and then electrical energy. The total energy input equals to sum of useful energy output and energy loss. Next is second law of thermodynamics. Application to solar energy. In solar thermal system, not all the absorbed solar heat can be converted into watts. The efficiency is limited by the kernel efficiency, which depends on temperature difference. In PV system, some solar energy is used as heat instead of being converted into electricity due to material and quantum limitation. Heat loss, reflection, resistance in wire, and imperfection in material are examples of entropy increase process.
Industrial application. First is solar power for manufacturing plant, used to generate electricity by installing solar photovoltaic PV on the factory rooftop or nearby land. The benefits are reduced electricity bills, low maintenance, and reduced carbon footprint. Second is solar thermal system for process heating. Solar thermal system can be used to heat water or produce steam in industries like textile, dairy, paper, and food processing. The benefits are reduced greenhouse gas emission, save fuel costs, and improve workplace safety. Third is solar desalination, used to evaporate seawater and condense it into clean water. Benefits: zero energy costs, reduce water bills, and useful in remote industrial zones. Challenge and solution. Challenge. First is low energy conversion efficiency. Photovoltaic panels only convert 15 to 22% of solar energy into electricity. Second, intermittency and variability. Solar energy is not always available because of the weather and day and night cycle. Third, it is material degradation. Long-term exposure to the heat and sunlight will damage the materials and reduce their lifespan. Solution: adopt multi-junction or perovskite silicon thermal cell, which are high efficiency solar cell to capture more sunlight. Second, use battery, thermal storage, or combine solar with other renewable source to store more energy. Third is use passive cooling, which is without using mechanical device device or active cooling, which is power system or mechanical component to reduce thermal stress, which will prolong panel life and maintain consistent output.
So, I am going to talk about case study of improving a solar water heater using thermodynamic principles. A flat plate solar water heating system was installed in residential house in Shah Alam, Selangor. After 6 months of use, the household report inconsistent water heating, especially during cloudy days or mornings. So, we can identify the problem that occurred, which water temperature rarely exceeded 45 degrees Celsius, even during hot afternoon. Suspected high heat loss through collector surface and pipe, and efficiency estimate at below 50% based on observed temperature rise and flow rate. So we use thermodynamic analysis in the first law of light. The formula is Q equals to M times Cp time change in temperature. So the answer we got is 1.254 kilowatt. In this case, the improvement that have been applied are replace standard glass cover with low ion tempered glass because it will increase solar transmittance by 8%. Applied black chrome coating to absorber plate for better heat absorption, and wrap hot water pipes with polyurethane foam insulation. And the result we can see after 3 weeks, outlet temperature increased to average of 53 degrees Celsius, heat loss reduced, confirmed via thermal camera inspection. System thermal efficiency improved from 47% to 65%, and users reported hot water available earlier in the morning and more consistent throughout the day. For the conclusion, this case proved that applying thermodynamic principles in a real-world solar system leads to measurable improvement. Even simple change in material and insulation can significantly boost system performance and energy saving in tropical climates like Malaysia.
My first recommendation is using the high-efficiency solar cells. High-efficiency solar cells are advanced photovoltaic technologies designed to convert a larger percentage of sunlight into usable electricity compared to standard silicon cells. For example, multi-junction cells, perovskite cells, or tandem cells. Next recommendation is hybrid solar systems. Advanced energy setups that combine 2 or more solar technologies or energy sources to increase efficiency, reliability, and sustainability. For example, photovoltaic PV systems with concentrated solar power with combined cycle. The third one is cooling technologies. Methods used to reduce the operating temperature of photovoltaic panels and solar thermal connectors. For instance, passive cooling, active cooling, or hybrid cooling. The last recommendation is smart grid and AI integration. It involves embedding digital technologies and artificial intelligence into the energy grid to optimize the generation, distribution, storage, and consumption of solar power. For example, real-time monitoring or AI algorithms. The first picture is about solar thermochemical conversion diagram. This diagram shows the energy flow and conversion in solar fuel systems. Next picture is about comparison of cooling techniques. This diagram shows how the passive or active methods manage heat and entropy in photovoltaic panels. Third picture is about overview of hybrid solar. This diagram that includes flowcharts and heat pipe cycles explain the flow through solar panels and heat sinks.
For the conclusion, thermodynamics play a crucial role in optimizing solar energy system. By applying the first and second law of thermodynamics, we can identify energy loss and improve overall system efficiency. Simple modifications based on thermodynamics analysis, such as better insulation, material selection, and system design can lead to significant performance improvements. This approach supports the development of more sustainable, cost-effective, and energy-efficient solar technologies. Therefore, thermodynamics analysis is a powerful tool to optimize solar energy system and support sustainable energy use.